A little bit more vocab for section 2. We have multiple zero and multiplicity. And I've kind of talked about multiple zero and multiplicity. If I back up, we had a multiple zero right there. -2 and -2 was repeated. Okay? That's called a multiple zero. Okay, so a multiple zero, like we just saw, is a repeated factor in a polynomial. If I have a repeated factor in a polynomial, then I wind up with a repeated zero, and that's what makes a multiple zero. Multiplicity is related to the multiple zero. The multiplicity of a multiple zero is how many times a zero is repeated in a polynomial. So like for that example that I just showed you, we had that -2 that was repeated. I saw a -2 twice. Therefore, the multiplicity of -2 was 2, because I saw it twice. Okay?
So wait, could you have like -2, -2, and then could you have like 2, 2?
Sure. Let me go back to that problem. If I had -2, -2, 2, 2, 2, and then 3, then the multiplicity of -2 would be 2, and the multiplicity of +2 would be 3. Okay? Does that answer your question? Okay. So let's go back to this. The key concept here is really kind of important for this part. How multiple zeros affect a graph. So we're talking about multiple zeros here. If A is a zero of multiplicity n, so what that means is A is a zero, so like that -2 on the previous problem, is a multiple zero of multiplicity n in some polynomial function. Okay? Then the behavior of the graph at the x-intercept that we're talking about, so at that zero, the behavior of the graph will be close to linear if n equals 1. If the multiplicity is 1, then the behavior of the graph around that zero looks like a line. If the multiplicity is 2, if n equals 2, then the behavior of the graph will be close to looking like a parabola. If the multiplicity is 3, so if n equals 3, then the behavior of the graph will be close to looking like a cubic function, a snake. Okay? So just close to that zero, the graph will look like a snake, or a parabola, or a line. It keeps going. So if you have a multiplicity of 4, then the graph will look like a snake with a bump in it. Okay, it'll look like a W or an M in that region, and so on. Okay, so that's what multiplicity does to a graph. Close to that zero, the graph will behave just like a polynomial with that degree. So it's kind of an interesting thing. So before we do this, actually, I want to go back to this graph right here. And I want to get our calculators out and actually graph this polynomial. So we don't have this stuff here. It's just this polynomial right here. I want to graph it, and I want to look at those zeros, especially this zero right here, the -2. Okay, so here's the graph. And notice we have that multiplicity at my -2, 0. We have a multiplicity of 2. And notice what the graph looks like in that little region right there. Just right here, it looks like a parabola. We have a multiplicity of 1 right there. And notice that just in this region right here, it looks like a line. And the same thing comes true here. The multiplicity for that 0 is 1. And within that little region near the 0, it looks like a line. Okay? Okay, so let's find the zeros, determine multiplicity, and describe how the graph behaves at those zeros. So we have this first guy here, x to the fourth minus 2x to the third minus 8x squared. What do we need to do? What? I want to do this algebraically without a graph. So we need to do what we did yesterday, which was factor it. So GCF here is not 2x, x squared. So I have x squared times what's left over, which is x squared minus 2x minus 8. Am I done factoring? No. What else? Good. Two numbers that multiply to give me negative 8, add to give me negative 2. What are they? Negative 4 and 2. So I get f of x equals x squared times x minus 4 times x plus 2. I want to find the zeros, so what does that mean I need to do now? So before you do that, the idea is that when you have zeros, the y-coordinate is 0, which means that this is my y-coordinate right here, so I'm making that 0. So I set the equation equal to 0, and now I can use the zero product property. What do I get? I get x squared equals 0, x minus 4 equals 0, x plus 2 equals 0. Technically what I have here with this x squared equals 0 is x times x. X times x equals 0. I can use the zero product property on that as well. And that gives me x equals 0, x equals 0. On this one I get x equals 4. On this one I get x equals negative 2. So find the zeros, we did. Determine multiplicity. Do I have any repeated zeros? I have this 0 right here is repeated twice. I have 2 of those, okay? So for x equals 0, the multiplicity for this guy is 2. The multiplicity for this one is 1. The multiplicity for this one is 1. Yeah, the multiplicity n is what they used here. Okay, so then describe how the graph behaves at these zeros. Well, with this 4th degree polynomial and a leading coefficient that's positive, I know my graph is probably going to look something like this. Okay? I have a 0 at 0, I have a 0 at 4, I have a 0 at negative 2. What is this graph going to look like when we get here? It's going to look like a parabola. Which way will that parabola be facing, up or down? If I have these zeros here, the 4 and the 2, and my graph is looking like this, then my parabola is going to cross here somewhere. It'll come back up to the middle 0 and turn back around and go back down and then come back up to the next one. So this parabola, actually, if I graphed it, my guess is it would be upside down. The point of this problem, though, is to say that this graph will look like a parabola near 0. What will the graph look like near 4? A line. And near negative 2? A line. Okay?
Oh, I see.
Next one, same idea. What do we do? Factor it, so I have f of x. GCF is x this time, times okay. Not done factoring, so keep going. X times x plus 2 times x plus 2. Do those add to give me negative 4? So yeah, so it's x minus 2, x minus 2. Negative 2 times negative 2 is positive 4. Negative 2 plus negative 2 is negative 4. Okay, now what? Set them equal to 0, and then use the zero product property. So I get x equals 0, I get x minus 2 equals 0, x minus 2 equals 0. So I get x equals 0, x equals 2, and x equals 2 again. I'm not going to rewrite it. Instead, I'm going to say that it has a multiplicity of 2. and on this x equals 0 has a multiplicity of 1. So, to find the zeros we did, determine multiplicity we did, describe how the graph behaves at these zeros. How does the graph behave here? Parabola. I should have written parabola, line over on that one. Parabola, P-A-R-A-B-O-L. And here, linear, near that zero only. Now overall, we see a third degree polynomial with a positive leading coefficient. So therefore, my graph is going to look something like this. Okay? I have a 0 at 0. I have a 0 at positive 2 with a multiplicity of 2. So what I'm going to do is I'm going to put my x-axis right there. And I'm going to call that 0, and I'm going to call that 2. Notice now that for that 0, it does look linear, even though this is just a sketch. And for that 0, I do see a sort of parabolic shape. Just in this little window right here, it does kind of look like a parabola. Okay? So I would expect the graph to look like this. In this little window right here, a line. Okay, we've already kind of talked about these two vocab words right here, relative maximum and relative minimum. If I draw a little sketch on here, it's just going to be a random, here's my some sort of function. These peaks right here are locally very, very close to those peaks. Those are maximum values. Each one of them can be called relative maximum values. So I'm going to call that peaks. So by peaks, I mean high points on a graph. Overall, we have a maximum of the maximums, which would be right here on this particular graph. That would be called an absolute maximum, but we don't need to know that here. Relative minimum is going to be these little valleys right here. I have two of them right here. Those are relative minimum. Within that little region right there, if you were a ball, you would collect down here at the bottom. Okay? Those are minimum values. Call them valleys. And my definition will be low points on a graph. To find a relative maximum or minimum, if you're asked to do so, or to find all of the relative maxima and relative minima, that's the plural for maximum and minimum, by the way. It's not maximums. You may use a calculator to graph the function. There is a way to do it algebraically, but you wouldn't learn that until you got to calculus. So we can't do that algebraically. But we can just graph the function and then find them on our calculator using the maximum or minimum operation on the calculator. So let's go ahead and do that. So here's a zoomed in version of the graph. Notice that my scale here on my y-axis has gone all the way up to 83 point something and down to negative 83 point something. And then what I did was I adjusted my x-axis so that the graph started to take up more of the window. I'm just trying to see more of this graph so I can see how it behaves. Notice that on this polynomial, if I were to have factored it, I would have seen a 0 here with a multiplicity of what? One. And a 0 here with a multiplicity of 1. And a 0 here with a multiplicity of 1. And I know that because in a very small window here around that 0, the graph looks like a line. The graph looks like a line. The graph looks like a line. Okay? So now I know that the multiplicity of those zeros can be seen and determined from just looking at the graph, which is another really valuable tool to have in your toolbox in this chapter. Anyway, we need to find any relative maxima or minima. So that's going to be peaks, there's one right there, and valleys, there's one right there. So to find that peak, that maximum value, I need to menu, analyze, maximum. And lower bound to the left side of that maximum, upper bound to the right side of that maximum, and it gives me that ordered pair right there. So that would be my answer if it was saying, what is the maximum? What is the relative maximum? I'd write down -4, 80. And then for the relative minimum, same thing. Menu, analyze, but this time minimum value. Left side of that minimum, right side of that minimum. There's my ordered pair, 2 comma negative 28. So the answer that I write down here is going to be relative maximum, and I'm abbreviating, rel max, that's fine, at the ordered pair, negative 4 comma 80. And then I'm going to say relative minimum. And if I had more than one, I'd write down all of those there. But I only have one here. It is 2 comma negative 28. So let's see if we can do the other one. So there's my graph, and I've already found the maximum and minimum values. So I'll write those down. I write max, or rel max, because it's not absolute maximum. And the ordered pair is negative 0.865. Notice there's no way we'd probably be able to find that by hand. So just go with the calculator. And then comma 3.13. And then relative minimum. Again, there's only one relative max and one relative minimum here. Parentheses 0.642, comma, looks like negative 2, is that right? Okay, so then there's your answers for those, just straight off the calculator. And if you had more, like if this is a 4th degree or 5th degree polynomial, and you happen to see like 2 or 3 peaks or 2 or 3 values, then you just write those down along with these ordered pairs for each relative max and each relative min. Okay, last thing in this section. The design of a digital box camera maximizes the volume. So we're talking about a box and maximum volume. This should sound kind of familiar to you guys. While keeping the sum of the dimensions at 6 inches. If the length must be 1.5 times the height, so for whatever reason, the design of this box says that the length has to be 1.5 times more than the height, what should each dimension be? We want a maximum volume with the sum of the dimensions of 6 inches, and the length must be 1.5 times the height. Well, it's going to be kind of hard to picture this unless I do what? Draw a picture. It says the design of a digital box. So I'm going to draw a box. And I'm going to try to make it 3-dimensional. So there's my box. The only thing I know about the dimensions is that the dimensions have to add to give me 6. So this length plus this length plus this length must be 6. Okay? Now, the only other thing that I know about this is that the length must be 1.5 times the height. Great. So what's the height? H. Yeah, we don't know it. So that's like the anchor dimension right here. The length must be 1.5 times the height. I don't know what the height is, so I'm going to call that H. As soon as I call that H, then what must the length be? 1.5 times H. Perfect. And now the sum of all the dimensions has to add to be 6 inches. The only other dimension I don't know is this one right here. If I take this plus this plus this, I got to get 6. Which means that this must be 6 minus H minus 1.5H. Because that's 6 overall. If I take away this dimension and this dimension, then I get this dimension right here. So then this can be written as 6 minus 2.5H. Okay? Now, how do you calculate the volume of something? Yeah, you multiply those 3 dimensions together for this box. So we have volume equals the height times the length times the width. There's your volume equation right there. Now the nice thing about this problem is you don't have to multiply this all back out. It doesn't say write me an equation in standard form. So you don't have to. Don't. Leave it like this, in factored form. Because this is a volume equation, then the graph that I see will be the volume of the box. What degree is this polynomial? The shortcut I taught you last time was to multiply all the h's together. H times h times h is h to the third. So it's a third degree polynomial. This will look like a snake. What's the leading coefficient here? Positive times negative. The leading coefficient here is negative. So my graph, when I graph it, should look something like that. Okay? Excluding end behavior, if this is the graph of volume, then where on this graph that I just drew is going to be the maximum? This peak right here. That's my answer, sitting right there. Okay? So let's go ahead and graph this polynomial, because that's the only way we're going to solve this problem. Graph it. There should be some sort of peak sitting there. Find it. As you enter this in, you want to type the times in between the parentheses. Otherwise, the calculator might give you some sort of error. Did it? And you don't want to use h like I just did. You want to use x, because it's a function of x. So x times, parentheses, 1.5x, parentheses, times, parentheses, 6 minus 2.5x. Close your parentheses, press enter. And it gives you that snake-looking graph with a negative leading coefficient. Of course, I need to zoom out some. So I'm going to grab my axes here and zoom out. And now I see that peak. So all I got to do is analyze graph, maximum value, left side, right side, gives me the ordered pair. There it is. Now we just got to figure out what that ordered pair means. So it gives me 1.6, 7.8. So I'm going to write that down. 1.6, comma, 7.68. The height is 1.6 inches, because the units here are in inches. What does the 7.68 represent? What was my equation? Volume. So that y-coordinate is the volume. So maximum volume equals 7.68 units would be inches, since this is volume, to the third. Does the question ask me for the maximum volume? No. What does it ask me for? The dimensions. So I have the height here. Now that I have the height, I can calculate the rest of it. I know that the height must be 1.5. Well, I know that the length must be 1.5 times the height. So 1.5 times 1.6 gives me 2.4. So the length equals 2.4 inches. And then the width must be 6 minus those. So if I add these two together, I get 4. 6 minus 4 is 2 inches. Just to check to see if I got that volume, I'm going to take the 2. So 2 times the 2.4 times the 1.6. And what should I see for an answer? The y-coordinate for that maximum value, 7.68. There it is. So that's how you do problems like this. When you guys did that box problem, the open top box of maximum volume, this is how I did it. So to finish off the problem now, well, I guess this is a new problem. What is the maximum volume of the camera if the sum of the dimensions is at most 4 inches this time? What do we do? Do the whole problem over again?
No.
Just substitute the 6 where? Yeah, in this original equation, now instead of 6 right here in my picture, it's a 4. So that means this becomes a 4, which means on my graph, all I have to do is go back to my graph, bring up my function, which is in my window right there, press over until I get to that 6. See, now it's going to be there we go. Up, now press over until I get to that 6, change it to a 4, and the polynomial changes for me. The maximum value stays there, and I wind up with an ordered pair of 1.07, comma 2.28. So now I know that the height of this one must be 1.07. The length must be 1.07 times that. So let me go back to my calculator. 1.07 times the 1.5 requirement, and I get 1.605, and then the width must be 4 minus that answer minus, well, I don't want to do that, 1.07. So the width must be 1.325, and these are still inches. And then what's that 2.28? Maximum volume. 2.28 inches to the third, in case you were asked.